a short review from the last lecture, where we finished the full description of the isometric group of the upper half plane, and described the geometric behavior of the orientation preserving isometries. And we introduced, we studied the Poincaré disk, and somehow the point is that the main results are easily established because somehow they have been already established for the upper half plane. And then the corresponding study of this geometric behavior, we saw how it looks like in the Poincaré disk. So first, a reminder that we had already proved, we had already obtained an explicit formulae for arbitrary Riemannian isometries of the upper half plane. We saw that that any such Riemannian isometry is given either as the Mobius transformation associated to a matrix in SL2R, or is given by a Mobius type formula. Actually, you see, as a kind of as a Mobius formula applied to the conjugate of the point we want to apply the isometry to, but with the matrix arising, having determinant -1, right? So in either case, an arbitrary Riemannian isometry is either given by a matrix of determinant 1 and then taking a Mobius formula, or by a matrix of determinant 1 and then taking a modified Mobius formula. And the point is that we proved this theorem. So this is kind of the first instance where we really have a full description of all isometries, and then that full description allowed us to describe the whole first the whole group of isometries that preserve the identity as PSL2R. We had already proved this inclusion, and then with this theorem at hand, one can easily deduce then equality. And then the next objective was to have a full description of the full isometry group in terms of a kind of a matrixly group, right? I mean, because you see, this equality, this tells us that this isometric group is almost a group of matrices. Right? I mean, one just has to mod out plus minus the identity matrix, but it's almost a group of matrices, and we want to have a similar presentation for the full isometric group. So we realize that this theorem can be stated as saying that there is a surjective function from the group of matrices of determinant plus -1 to the full group of Riemannian isometries, right? That in the case of determinant 1 associates this this isometry, and in the case of determinant -1 associates this other isometry. Its surjective is part of the statement of the theorem, and then it's actually a group isomorphism. So one actually obtains this. One obtains. Okay, here this isomorphism, right? By just modding out the kernel of this group homomorphism, which is plus or minus the identity. So this so with this isomorphism, we are presenting the full isometric group. We are showing that it's almost a group of matrices, right? It's almost this group of matrices, except that again one has to mod out plus minus the identity, right? So it's almost a group of matrices of determinant plus or minus 1, except that for an isometry we cannot distinguish between a matrix and minus itself, and minus the matrix. Okay, and then and even more, and then the next step is to describe this group entirely in terms of PSL2R. That's like the one of the ultimate goals of last lecture. And for that, we first realize that this group of matrices of determinant plus or minus 1 is a non-trivial semi-direct product of SL2R with plus minus 1. And the whole point is that this short exact sequence splits, right? And here this is the splitting. By split I mean that there is such group homomorphism from kind of from the last group in the sequence to the one in the middle, such that this composition is the identity of the rightmost group. Yeah, and also just the section, this splitting, this what it tells me is the relation it has with the semi-direct product structure is that somehow the point is that one defines an action of this group on this one by saying the action of an element here. So let's say the only non-trivial element here is by conjugation by the value of S at it. So that's the relation between the splitting of a short exact sequence and the semi-direct product structure of the group in the middle. Right? So, right. So this presents S star L2R in terms just of SL2R. And the next thing is that one can easily see that this splitting descends to the quotient when we mod out here and here, plus minus the identity. Right? So this same section somehow works to split this short exact sequence, and that then presents PS star L2R as a semi-direct product directly involving PSL2R, which is the group of orientation preserving Riemannian isometries. And so all the discussion is summarized in this corollary. And so something I want to convince you of is you see that one has like this group that is a priori defined in just abstract terms, and one is presenting it in a very concrete way. That's kind of the idea I want to convey, that this corollary allows me to think in very concrete terms of this group. Okay, then we moved on to discussing the geometric behavior of the orientation preserving Riemannian isometries. So recall that in PSL2R does not contain loxodromic elements, right? Simply because a loxodromic Mobius transformation never preserves a disk bijectively, and this group is precisely the group of Mobius transformations that preserve the disk U bijectively. U is a disk in C bar, right? So it cannot contain loxodromic elements. So one moves on to just studying the geometry of possible parabolic, hyperbolic, and elliptic elements. And then in the parabolic case, we saw that the fixed point has to lie on R bar. It could be infinity, and the transformation looks like. But so here you see, here you have these circles, that are stable under the action, and these are shortest curves, right? And the image of one such is another one such. Now in the hyperbolic case, the two fixed points lie in R bar, and then somehow the iterations of the hyperbolic Mobius transformation look like flowing from one point to the other, so from the repulsor to the retractor, to the attractor. Sorry. So here, if the attractor is Z0 and the repulsor is Z1, somehow the iterations of nu look like flowing in this direction. And what you are seeing here are curves that are stable. Each of them is stable. They are not shortest curves, right? Only one of them is shortest curve, which is the one which is a segment of a common circle that is actually orthogonal. Yeah, and then somehow the flow is like for instance, if you take a shortest curve here, which would be in the orthogonal family to the orange curves, or in other words, would be a segment of an Apollonius circle of the two fixed points. Such shortest curve goes to another one, 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 and that's somehow the behavior, going away from the repulsor and moving into the attractor. And finally, in the elliptic case, one shows that the two fixed points of the elliptic Mobius transformation, one of them has to lie inside U, the other one outside U, and they have to be conjugate complex numbers. And the elliptic transformation is somehow a rotation around the fixed point lying in U. And you see the Apollonius circles of the 2 points, of the two fixed points, that lie, the Apollonius circles that are completely contained in U. Well, we saw already that each one of them is stable under the action of the Mobius transformation, but now one can also see that each one of them is a hyperbolic circle with center that fixed point, and that is somehow how one finally has kind of the full picture of rotation, that the elliptic transformations are rotations actually around the fixed point. Okay, and now let me say a bit about the Poincaré disk. In the Poincaré disk, well, I just recalled how one gives the Riemannian metric for the Poincaré disk by just pulling the Riemannian metric of the hyperboloid through stereographic projection. We saw that there is a formula, and then using the fact that we also have this biholomorphism between U and D, and the fact that the Riemannian metric that we put on U was defined by pulling this Riemannian metric on the disk to U through this Mobius transformation. That is, using that the Riemannian metric on U was defined precisely to make the Cayley transformation Riemannian isometry between U and D. We can simply transfer everything we know about the upper half plane to the Poincaré disk. So that's pretty much what we did. And so you see, in particular, compute the group of the full group of Riemannian isometries that preserve the orientation. And also we can give a full description, you see, explicit formulae for all possible Riemannian isometries of the Poincaré disk. So they are either given by Mobius transformations that preserve the disk bijectively, or they are given by some modified Mobius formula. And then also mapping, transferring our knowledge of shortest curves on the upper half plane and circles in the upper half plane to the Poincaré disk, one obtains that the shortest curves in the Poincaré disk are precisely the segments of circles in C bar that are perpendicular to the complex unit circle, and that is simply because under Cayley transformation, R bar goes to the complex unit circle, and being a Mobius transformation, the Cayley transformation brings circles in C bar to circles in C bar, and preserves angles because it's conformal. Okay, and same thing about the circles. Well, the Cayley transformation is a Riemannian isometry, so it's also a metric isometry. So it takes hyperbolic circles to hyperbolic circles, but we know that the hyperbolic circles in U are precisely the Euclidean circles in C bar contained in U. So their images are Euclidean circles in C bar contained in D. Okay, and finally, the geometric behavior of the orientation preserving Riemannian isometries of the disk, and this is where I think it's just better to see the animations that I was showing here. So here you can see the parabolic case, as I was saying. Fixed point has to lie on the complex unit circle. Hyperbolic case, the leftmost one, and you can really see here how the iterations really look like flowing away from one of the fixed points towards the other fixed point, and that the fixed points lie again in the unit in the complex unit circle, and the elliptic case. Here you can see the fixed point of the Mobius transformation that lies inside D. Right? The other one we are not seeing it, but you can really see here that it really behaves as a rotation. Okay, and so that's the review. So let's